And today's speaker is Professor Giacomo de Palma. He received his PhD in 2016 in physics from Scuola Normale, Superiore in Pisa, Italy. And then he moved to the University of Copenhagen, Denmark, where he was between 2016 and 2019, first as a postdoc and later as a Marie Curie Fellow. And then in September 2019, Giacomo moved to do a postdoc in Seth Lloyd's group at MIT. And this is where I met Giacomo, and we went out and had very, very nice dinners on a couple of occasions. And now in March 2021, Giacomo secured a tenure-track professorship in mathematical physics at Scuola Normale Superiore, Pisa. So with this, we're very, very happy to have you here, Giacomo. Please take over the virtual floor.
Okay, so thank you very much for the invitation and for the nice introduction. Let me share screen. Okay, do you see slides and my cursor?
Yes.
Okay, great. So I will present, I have roughly 30-35 minutes, right?
Yeah, the kind of the strict deadline is that we need to be done in an hour with questions and everything. So just go as you feel.
Yeah, great. So I will present this work about exponential quantum advantage in the analysis of linear differential equations. And this is a work in collaboration with the research group of Seth Lloyd at MIT. So it's a work with me, Seth, and then Bo Bacchiani, who is a PhD student in the group, who has recently given a seminar in this series. And then Dirk Englund, a professor, and William Kaminsky, who is associated to the group, and Milad Mardian, who is now assistant professor at the University of New Mexico. And this is the archive reference for this talk. So let me start. Quantum machine learning is one of the most promising applications to actually show some practical application of near-term quantum devices, of these NISQ devices that will be hopefully available in the next few years. And one of the main algorithms in quantum machine learning is an algorithm that can achieve a potential exponential speedup in the principal component analysis of matrices with low rank. And the way this algorithm works, let's assume for simplicity that the matrix that we want to analyze is an Hermitian matrix. Then roughly the idea is to implement this matrix as the density matrix of some quantum state. And then it's possible to apply a technique that is called density matrix exponentiation, that from the given copies of this quantum state with a given density matrix can implement this density matrix as a Hamiltonian and apply it to some input pure quantum state. And this technique can achieve an exponential speedup over the standard classical techniques for principal component analysis when the rank of the matrix is low, in the sense that there are few eigenvalues that dominate the singular value decomposition. So what are this algorithm has some drawbacks. The first obvious thing is that we need to be able to implement this the matrix to be analyzed as the density matrix of a quantum state, and then depending on what it is, this will have a complexity. And actually, the major drawback of this algorithm is a series of recent results, mainly by Yu and Tang. And these results are actually classical algorithms that are inspired to this quantum algorithm, and that can, in a purely classical way, can exploit the fact that the matrix to be analyzed has a small rank, in the sense that there are few eigenvalues, few singular values that dominate over all the others. And you can exploit this to build a new probabilistic classical algorithm for principal component analysis that also has an exponential improvement in the runtime with respect to the standard algorithm, that classical algorithm that is employed. And so here, after the publication of this fundamental result by Wing-Tang, okay, this series of results is called Dequantization, because the main idea is to take inspiration from the quantum algorithms to design new classical algorithms that achieve an analog, a similar speedup. So after the series of results, it was for a bit, it was unclear whether the quantum algorithms with density matrix exponentiation can still have some significant advantage over these new classical algorithms. So now let me move to a different problem. Like we talked about principal component analysis, now we go talking about solving linear differential equations. And there has been this seminal result by Andrew Childs and collaborators that have found some quantum algorithm to solve linear differential equation with a potential exponential speedup in the dimension of the system. So this algorithm will have a significant speedup where the linear differential equation involves a vector with high dimension, and this algorithm promises an exponential speedup in the dimension of this vector. The caveat of this quantum algorithm is in the way the solution to the differential equation is provided, because the solution of the differential equation here is provided as a quantum state, in the sense that the solution is a vector, and up to a normalization constant, we can assume that this vector has norm 1. And so this vector is an element of some Hilbert space and can be considered as a quantum state. And this is exactly the way this algorithm produces the output. So the main issue of this way of producing an output is then how to read the solution, how to extract information from the solution. Because of course, in principle, we can do tomography on the output quantum state. But then if we want to perform full quantum state tomography, this would require a runtime that grows usually it's quadratic in the dimension of the Hilbert space, and therefore this will erase the potential exponential speedup of the algorithm. And then this algorithm can actually have this exponential speedup over the classical algorithm, only if we find a clever way of extracting the information from the output. And in particular, we will not be able to extract all the information about the output, but we will need some scenario where only some partial information on the output is needed, and there is a clever way to extract this partial information from the quantum state that is produced by this algorithm. So actually, I presented you two algorithms in quantum machine learning, like the algorithm on differential equation as the trouble of how to extract information from the output, while the algorithm on quantum principal component analysis has the issue on how to produce the input quantum state. And then the idea of this work is that, okay, we have two problems, but actually we can put together these two problems, and from two problems we get one solution. So the idea is that we use this quantum state that is produced by the quantum solver of ordinary differential equations, and we plug in this quantum state as input from the quantum principal component analysis. And as we will see in the remaining part of this talk, putting like this, putting together these problems actually solves the issues of both these quantum algorithms. So let's first see a bit more in detail how the quantum algorithm for linear differential equation works. So let's say that we have some linear ordinary differential equation where the unknown function to be found takes values in Rn. And of course, we want n to be much bigger than 1 because we will have an exponential speedup with respect to n. And this exponential speedup is significant when n is large. So we can write this equation in the form the time derivative of x is equal to a matrix A times x plus some constant vector b. And actually, in order for the algorithm for linear differential equations to be efficient, we will need A to be sparse. And being sparse means that each row and each column of A only have a small number of entries that are non-zero. So this S is the sparsity of the matrix and denotes the maximum number of entries in a given row or a given column of A that are different from 0. So we denote with this capital T the final time up to which we want to run this differential equation. And another assumption that we will need is that the eigenvalues of A must have a negative real part, because if these eigenvalues have a positive real part, then the solution blows up exponentially with time and starts being unstable, in the sense that small perturbations in the initial condition can be exponentially amplified by the time evolution, and this makes the system unstable, and we want to avoid this situation. So this algorithm works by discretizing this time evolution in intervals that have a step that's roughly equal to the inverse of the operator norm of this matrix A. And we will denote with capital K the total number of steps in this evolution. So actually, the algorithm by Andrew Childs is quite complex and involves a series of tricks that allow to improve the runtime. And here, for simplicity, I will just present the basic idea that lies behind that algorithm, over which you can apply the series of tricks to improve the runtime. So the idea of this algorithm is that we want to build what is called a quantum history state. And a quantum history state, there are two registers, a system register and a so-called time register. And what we would like it to be is a coherent superposition of the solution of the differential equation at several times that are spaced by this time interval delta t. So here we have this coherent superposition from time 0 to the final time of the differential equation. And actually, the way that we enforce the differential equation is that we enforce it as a condition on this quantum history state. And the condition on this quantum history state that results from the differential equation is that if we apply this matrix M to the quantum history state, we get this simple state that we see in the right-hand side that depends on the initial condition of the differential equation and on the constant offset vector that appears in the differential equation. So roughly speaking, the quantum history state can be obtained by applying the inverse of this matrix M to this state that depends on the initial condition. And the rough idea to apply this inverse of the matrix M is to use the quantum algorithm for linear systems of equation, the one that is known as the HHL algorithm, from the initials of Harrow, Hasidim, and Lloyd, who are the authors who proposed this algorithm for solving linear systems of equations on a quantum computer. Okay, this is the basic idea that underlies the algorithm for linear differential equations. So let's see what is the runtime of this algorithm. Here it is. It involves this kappa, and this kappa is related, depends on this matrix A, and in particular, it depends on the condition number of the matrix V that is needed to diagonalize A. So here we see we diagonalize A with by conjugating it with a matrix B, and this kappa is the condition number of that B. Then the runtime grows linearly with the time over which we want to run the differential equation, and grows linearly with the operator norm of A, and also with the sparsity of the matrix A. And this tilde over this O means that logarithmic factors have been suppressed. So actually here you will have also factors that are proportional to the logarithm of this quantity. And the important part is that in this quantity here, the dimension of the solution, so this capital N, does not appear in any way. So it may appear indirectly in this condition number or in the operator norm of A, but there is no, it does not appear explicitly. So in principle, if this condition number and the operator norm of A stay fixed, even if we send this dimension capital N to infinity, there will not be any significant change in the runtime of this algorithm. Okay, then the idea is the following. So we apply this quantum algorithm from Andrew Childs and co-authors, and we get this quantum history state for the differential equation. And then we want to apply the algorithm for principal component analysis to this quantum history state. So the idea is that we want to perform a Remit decomposition of this quantum history state, and we will use, like I told you, that this principal component analysis algorithm requires a density matrix as input. And actually here we can use as density matrices the marginal states of this psi on the system register and on the time register, and we can apply density matrix exponentiation to these marginals. And actually, if you want to see what these marginals look like, so the marginal on the system register, it's just a convex combination of the solution of the differential equation at several times. And the marginals at the time in the time register, it's a bit more complex. It's not diagonal in the canonical basis, and it depends on the overlaps of these solutions of the differential equation at the various times. And on the, still looking at the time part, we can not only do principal component analysis to find the singular vectors and singular values of this, so the eigenvectors and eigenvalues of this matrix, but we can also, for example, apply Fourier transform or wavelet transforms. See how this, how we can apply it. And as an example to apply all these techniques, we have chosen continuous time Markov chains. So these continuous time Markov chains provide a mathematical model for the dynamics of complex networks. So for example, they can model the spread of diseases, which is a topic that is extremely actual in this period, or they can model, for example, the spread of opinions. And the model of this complex networks is, so this network we assume that is made by small n nodes. And so these nodes may represent, for example, people. And each node can be in a discrete set of states, and the small q will be the number of possible states of each node. So for example, a person can be susceptible to a disease, or can be ill, or can be recovered from the disease. And of course, the total number of possible states we denote it with capital N, and will be q to the small n, because we can choose independently the state of each node. And then in this case, we can associate to this x of t appearing in the differential equation that we have seen before, the vector of all the joint probabilities of these capital N possible states of the network. And then in this case, if I go back to the differential equation, B will be 0. And so this X will be the probability vector, and this capital A will be the matrix of the transition rates between the states of the chain. And actually, in all the typical scenarios, this matrix of transition rates is actually a sparse matrix, because in a single step, we do not expect many nodes to change state. So, and of course, as I was telling before, an example can be the spread, to model the spread of diseases. And actually, since we are going to perform classical simulations of this quantum algorithm, to reduce the computational complexity of these simulations, we reduce the number of states of a node to 2. And this corresponds to the model for epidemics, where a given person can be either susceptible or infected. So we neglect, for simplicity, the recovered state. And we claim that we assume that recovered people are susceptible as people who had never got the disease. Okay, so this is the simulations that we are doing. So here you can see the network that we are employing. So there are, as you can see, 6 people, and this this links denotes which people can infect which other people, and the thickness of the edge denotes the probability that, for example, this is a thick edge, so there is a high probability that person 0 can infect person 1, or vice versa if one of them is ill, while thin lines denotes a low probability of infection. So here are our simulations. Here you see the time in days. Here you see on a grayscale the probability of a given state. And here you see all the possible state of this network. And the color code is that dark blue means infected person and the light blue means susceptible person. So here you see all the possible states with the time behavior of the probability of being ill in the evolution of the chain. Okay, so let's do, so we can build on our simulation of the quantum computer, this quantum history state. And then let's perform the first analysis that I mentioned, that is the Remit decomposition. So we find the singular vectors and singular values. Here are the singular values, and this is a logarithmic scale. So you can see that they decrease exponentially and they are negligible after a certain value. So this matrix satisfies the low rank assumption that is required for the quantum principal component analysis to be efficient. Here you see the plots of the time part of the singular vectors. So notice that the 0 is here. So you will have this vector 1 that is always different from 0. This is the one associated to the stationary state. And then you have all the other vectors with, like, these are the first, like the 4 vector with the larger singular values. And here you see the system part of the singular vectors, like the colors are the same that on the plot on the left-hand side. So here you see the state with the same code as before. So dark blue is infected, light blue is susceptible. And on the right-hand side, you see the values of the singular vectors corresponding to the states. So 0 is here. You can see that the blue vector dominates, and in particular, it has large components in the state where everybody is susceptible and where everybody is ill. And you can see the decline in the singular values because the other vectors are have much smaller components than the blue and the orange vectors. Okay, then we can, like, looking at the time part of this equation, this quantum algorithm and also gives us information on the power spectrum. This is the global power spectrum, which of course has a peak in frequency 0 because this is the stationary state of the system. And this is the power spectrum of each singular vector for the first 4 singular vectors. So here we can see that the first singular vector, that is the blue one, is associated to the stationary state and then has a peak at frequency 0, while all the other singular vectors, of course, have small components associated to the frequency 0 and have higher components associated to other frequencies. Okay. So another possible kind of analysis that we can run is wavelet transform. So here are the plot. So this is an analysis on the time domain, of course. And here are the plots of the wavelets that we are considering. So from the 0th wavelet to this 7th wavelet. No, so actually, we consider 15 of them. Sorry, we also have these other ones in the second plot. So we have 16 wavelets. And here are the, like, how much these wavelets are present in the global time behavior of our solution. And actually, we see that the probability decreases, like the weight of a given wavelet decreases exponentially with the wavelet number. And here we see what happens for each singular vector among the first dominant 4. So we see, okay, the zero of this plot is here. So for the blue singular vector associated to the stationary solution, we have a high overlap with the zeros wavelet, and then the small overlaps with all the remaining ones, while the following singular vectors have high overlaps with the next wavelets. Okay, so actually I am like one question is like I presented this algorithm as a solution to keep the quantum exponential speedup over classical algorithm, including the new algorithms that come from the dequantization of principal component analysis and density matrix exponentiation. So then you may wonder whether we can show that there is no like simple modification of the dequantization algorithm that allows us to get in a purely classical fashion the principal components of the solution of this differential equation. And actually the answer to this question is no, and I will now try to convince you that this is the case. So the way this algorithm for quantum, that this dequantized algorithm for principal component analysis work is that instead of looking at the whole matrix of which you want to find the singular vectors and singular values, you sample some from the entries of this matrix, and the main property that this algorithm exploits is that if the matrix has low rank, then it is enough to look only at a small fraction of all the entries to be able to find good approximation to the singular vectors and the singular values. And then you will not need to sample it for a number of times that's proportional to the number of entries of the matrix, but it will be enough to sample an exponentially small number of times. But now the point is that, I remind you here that we are doing a principal component analysis on the quantum history state, and the quantum history state is the output of the quantum algorithm for the solution of linear differential equations. So we do not have directly access to the entries of the state. And this is why we are not able to directly apply this dequantized algorithm, because we do not have the entries of the matrix of which we want to find the singular vectors and singular values. And actually, these entries of this matrix are related to the probabilities of getting a particular configuration of the system at a given time. So let's see more in detail what these entries of this matrix are. And for this, I will denote with capital W of t the random state of the system at time t. So this is a random variable that can have capital N possible values. And then let's look at the marginal of the quantum history state on the time side. And then it is possible to show that the entry of this marginal corresponding to times t and t prime is proportional to the probability that given two independent Monte Carlo simulations of our system, the state of the first simulation at time t is equal to the state of the second simulation at time t prime. So let's see, in principle, we can try to estimate this quantity with Monte Carlo algorithms, but the point, the main issue is that if the only thing that we can do is to perform several Monte Carlo simulations of the time evolution, and then check when we get a coincidence between like some simulation at time t and some other simulation at time t prime. But the issue is that this probability can be exponentially small in the number of possible states. And if this is the case, we will never be able to see such a coincidence. And then if we are not able to see such a coincidence, we will be forced to approximate this probability with the trivial estimate that is 0. And then we will get a trivial estimate for the singular vectors and singular values of this matrix, because we will approximate this matrix with the identically 0 matrix. And actually, if you want an estimate for how many times we need to run the simulation before seeing such a coincidence, this is, of course, order 1 over the probability of seeing such a coincidence, that is the scalar product between the probability vector at time t and the probability vector at time t prime. And this scalar product by Cauchy-Schwarz is clearly upper bounded by the square norm of the, like by the product of the norms of these probability vectors. And this, then this number of times is clearly lower bounded by the inverse of the maximum square norm of the probability vector over all the possible times. So if at every time the probability distribution is widespread over many states, so if the support of the probability distribution is exponentially large at all times, the probability of seeing such a coincidence will always be exponentially small, and then it will always be exponentially like the complexity of finding even a single entry of this matrix with classical Monte Carlo simulations will grow exponentially with the number of nodes in the network. Okay, so I can finally come to the conclusions. We have shown a proposal for a quantum machine learning algorithm that solves at the same time the issue of the dequantization. So it's not, you can't do in an efficient way on a classical computer what this algorithm accomplishes. So there is an actual quantum advantage, and does not require a quantum random access memory, because the input for the machine, the principal component analysis algorithm, is exactly the output of the quantum algorithm for linear differential equations. And this, so this algorithm to analyze the solution of linear differential equations can have several applications in the domain of continuous time Markov chains, for example, in epidemiology or for the spread of opinions, or like, since linear differential equations are ubiquitous in all fields of science and technology, there's an enormous possible set of potential applications for this algorithm. And finally, let me mention that we have recently extended the algorithm to solve linear differential equations to nonlinear equations in this other paper. So also in this case, we can put together the pieces, and then this algorithm can provide an algorithm to also analyze the solution of a nonlinear differential equation. So that was all I wanted to tell you. Thanks for the attention. I'm waiting for questions.
Thanks a lot, Giacomo. That was really, really, really nice to see. Let's see if we have any questions. If you do have questions, press the raise the hand button, or pop your question into the Q&A button. Perhaps whilst people do that, it's a bit of a kind of maybe technical question, and maybe you did answer it, but so initially when you were kind of telling us the time complexity of your algorithm, you said like it scales like linearly with the sparsity of the matrix or the rank of the matrix, and it scales with the condition number of the matrix, and like not like there's no n exponential number appearing anywhere. But what kind of problem? So I can see places where, you know, the condition number would scale poorly with n. So what kind of problems do you have nice scalings of the condition number with n?
Okay, so like the trivial case that you can see is that if this matrix A is Hermitian, then you can diagonalize it with a unitary matrix, and this condition number is 1. Because like I remind you that this is not the condition number of A, but is the condition number of the matrix that you need to diagonalize A.
Okay.
So if A is Hermitian, then this is roughly unitary. So if Hermitian or anti-Hermitian, you can diagonalize it with a unitary matrix, and this condition number is 1. Mm-hmm. Then more or less you would like, or in general, if the eigenvectors of A are orthogonal, then you can still diagonalize it with a unitary transformation, and this condition number is still 1. Right. So you like the nice situation is the situation where the eigenvectors of A are almost orthogonal, or still you do not have eigenvectors that are almost parallel. Then we are like exploring what are like possible scenarios where this can happen, but like I don't think this, okay, of course this will rule out some scenarios where you can have that the eigenvectors of A may be exponentially close to each other. But I'm still convinced that this is not a heavy limitation, in the sense that there will be several other cases where the eigenvectors of A behave nicely and are, even if not orthogonal, they are not close.
Right. Thanks. I think we have a question from Professor Mike Payne, and then after Mike, we have a question from Professor Stefan de Bievre.
Okay, right. Well, thanks very much. I mean, it's very interesting. I just have one thing I can't quite get my head around, that if we set delta t to 0, then we get a whole series of states which are the same. I know they've got a different index I on them, but I'm just slightly concerned about how that sits with the no cloning theorem.
Okay, but actually, maybe I didn't say it in a precise way, but the one thing is that this, like this delta t, it can't be chosen. If we want the algorithm to work, we have to choose this value. So this is not a free parameter that we can tune. Okay. So the algorithm will require delta t to be the inverse of the, or close to the inverse of the operator norm of A.
But I mean, that's normally just for stability to get, isn't it? Or is there some more fundamental reason why, if you chose a smaller value of delta t,
actually,
you're kind of time generating states, and presumably, you know, you can set delta t whatever you like. Agree if it gets too big, then you're going to have problems because you've lost accuracy. But what's the reason why you can't have delta t going to 0, just formally?
Okay, the reason I didn't see all the like present all the details of this algorithm, but the point is that if you reduce delta t, you will increase the number of steps, and then in the way this algorithm is precisely working is that you can write an analytic solution to this equation via matrix exponential, and the algorithm truncates the matrix exponential with a Taylor series. So at each step, there is, like, since the Taylor series is truncated, there is some error that is committed. And since these errors at each step accumulate. If delta t is too small, these errors become dominant, and you will get a bad error in the end. So roughly the idea is that if you have too many steps, then the error increases, and you do not want too many steps for this reason.
Yeah, I understand the numerics of that, but I'm just concerned about what looks to be a possibility of creating numerous copies of states. I know they're entangled with an index I. I'm just wondering what, if there is any issue with the no-cloning theorem, and whether that produces any restrictions with the states you end up with.
Okay, here I don't think there are issues with the no-cloning theorem, because this is actually a coherent superposition, so you do not have all these copies. Like, for example, an easy way where you can imagine that you can create a state like this. Let us assume that the evolution is discrete and it's given by a unitary. Then let's say that you get your input state that will be the initial state of your evolution. And then you append a time register that is in a coherent superposition of several number of steps. And then you apply this operation. In a coherent way, you read your time register, and then you apply the unitary to your state the number of times that you have read in the time register, and you create exactly this state. So here you're not making copies of the state, because you're not, this is not a tensor product. So this state exists in a coherent superposition, and then you can't have two of them together at the same time. I don't know if this answers.
Yeah, okay, I will think about it. Thank you.
Okay, let's see if Stefan is on the call.
Hi.
Hi, Stefan.
Hi, I'm here. Well, actually, Professor Payne just asked my question, which is quite nice. So I have a slightly different question then. If you fix k and n, how many qubits do you need?
Okay.
You want to run this on a quantum computer, I understand. So how many qubits do you need to run this?
I don't. You will need a number of qubits to store this state. So this will be the logarithm of capital N to store this system state. And then the qubits for the time register, that will be logarithm of capital K. And then you need some ancillary qubits, but I don't think you should not need you don't get, it's not worse than a constant overhead on what I just said. So the number of qubits should be logarithm of capital N plus logarithm of capital K times at most a constant overhead.
And so suppose you do that, and now if you talk to a numerical analyst who will ask you about how you control convergence and accuracy, what will you answer to him? Because he will want to take k to infinity, actually. Yes, to infinity. And you just were explaining that this cannot really be done. So how do you control accuracy, and how do you compare the accuracy of your algorithm to that of completely standard algorithms?
Okay, I have not included it in the slides, but in the paper you can find the precise estimates for the accuracy of this quantum history state. So this is something that has been done. And actually the reason why here you do not see any dependence on the accuracy is that it's a logarithmic scaling. Like if you, your output will be some normalized quantum state. So if you want to produce a state that is epsilon close to the exact quantum history state, then you get a scaling that's logarithmic in 1 over epsilon in the complexity. You can also see it from the title of the paper that presents this this algorithm for linear differential equation. You have an exponential improved dependence on precision in the sense that the runtime scales like a logarithm of 1 over epsilon. So if you want to be a bit more precise and remove this tilde, you should add a logarithm 1 over epsilon here.
Okay, thank you.
Let's see, do we have any other questions? We still have 1 or 2 minutes. If not, I might ask a question myself, Giacomo. So on the first kind of slide where you showed simulations.
Okay, here.
Here, when I look at the time axis, things look constant in time. I think I'm completely misunderstanding how to read this figure.
Okay, maybe this was a bit a bad choice of how to make the picture. Because like what maybe they like we are making a new plot, new version of this plot involving a longer time interval, because actually what is supposed to happen is that the color should change on the horizontal axis even if you don't see it, because it changes only a bit.
Okay, so yeah, actually maybe on the top line.
Like color is supposed to change from left to right.
Oh, okay. I think I see some lines where it changes now. Okay.
Like for example, in these lines here, you see that something happens.
Right.
Like this state becomes less likely.
Yeah, that's right.
And like here, you see that something is happening.
And do you know how many qubits you guys simulated to do this?
I don't remember the precise figure for this.
So kind of what I'm interested in actually is how much noise could you have on these qubits to kind of run something like this? Like, have you played around with any?
We didn't really play with noise. Actually, I think that like I don't expect this to be much robust with respect to noise, in the sense that usually when you have like here you have quantum PCA with phase estimation, like density matrix exponentiation and phase estimation, and usually phase estimation is not robust to noise, in the sense that you would like to be close in trace distance to the ideal state. Yeah. Otherwise you mess it up.
Yeah. Okay.
So given that current quantum computers are quite noisy and don't have ideal states, how far away are we from running these kinds of algorithms on existing quantum computers? Would they have to be perfect before we can run this kind of stuff?
Probably some noise can be tolerated, but my guess would be that some form of error correction would be needed.
Okay. And then on the question of qubit number and scaling, do you think these small problems, so this sort of infection network, you have 7 nodes, and there are quantum computers that exist now with in the dozens of qubits. Is a small network like this possible to actually run on a real quantum computer now, or are we still far away from this?
The main issue is the noise for this.
So computers are still too noisy to run this kind of
I would say so. Like here, like we have been limited to 7 qubits, because like if you, otherwise the classical simulation becomes too computationally expensive.
Mm-hmm.
And we are not being like, you can't run simulation on too many qubits, because otherwise it will take forever to run.
Mm-hmm. But yeah, okay.
But still, I would say that like the main, if you want to implement this on a real quantum computer, the number of qubits will not be an issue. I don't think there will be a high requirement. Okay, of course, as soon as you can, as soon as you can store your probability vector state. So at least you need, like, the number of qubits should be the logarithm of capital N, and of course they should grow linearly with the number of nodes, and this is unavoidable. So this may be challenging depending on what your network is. But otherwise, if you want to implement it on a small scale, noise will be the main issue.
Okay. And there are currently no avoidable techniques. We can't just run this many, many times and get some sort of average to get an estimate and slowly reduce our error.
This may work, like, actually, this, like, would be a good idea to make simulations in this direction, to, like, inject some artificial noise in our simulations and see how fast the result degrades. So this is something that we are looking at.
All right. Well, thank you for this talk.
Yeah,
Thanks
so
for
much,
listening.
Giacomo. This was really interesting, a great kind of end of the academic year's seminar series.